Yeah, it's recording now. So, so this lecture will be recorded, and also it will be. Yeah. Okay. So it will be. Where am I here? Should report, return to session. Okay. So now let me start by first of all going to the first slide. There's going to be some delays here and there because this is the first time that we do this, but bear with me. Okay, so our lecture is a continuation of what we did last time, but before I do that, there are two things. One, at 11:30, at exactly 11:30 on UAE time, we have to stop and stand for 2 minutes silence for the martyrs. Today's Martyrs Day of the UAE. So at exactly 11:30, we will just stop for a minute and for 2 minutes, in fact, and then maybe read some dua or something for the Martyrs Day. So that's the first thing. The second thing that I wanted to start with before I continue with the lecture is there were some questions about the exam, which I need to go over. I actually reviewed the notes that you guys gave me, and there are a couple of things that I wanted to make sure we discuss before, just so that you understand with it. The first one is question number 2. I think everybody sees question number 2. I'll just make it a little bit bigger. Question number 2, which talks about, I actually canceled this question. If you remember, I just took it out and it did not count. So in here, and the reason I canceled this question out because it was missing some information. Because what is it telling you? It's telling you there are two capacitors, parallel plate capacitors, capacitor A and capacitor B. So there are two capacitor A and capacitor B. And he's telling you that the dielectric material in both of them, one of them is K kappa and one of them is twice that. Now, the missing piece of information that I did not give to you is let me just go to the whiteboard here. So the missing information that I did not give to you is the fact that C0A, I should have said that C0A is the same as C0B. That means the initial capacitors at the beginning, so the geometry, basically the geometry of the gap and the area is the same. I did not tell you that in the question, and because of that, obviously you cannot answer the question. So anyway, so assuming that I tell you this, I tell you that the capacitor, the initial capacitance for dielectric or for parallel plate A is the same as that, then what happens, then you say, okay, then my new capacitor A, let's just call it CA, will be equal to kappa A C0. And the new capacitor for CB will be kappa B C0. Okay, sorry, C0. So if you do that, and knowing the fact that, let me just get my piece of paper, sorry. Yeah, knowing that the question told you that kappa A is equal to twice kappa B, then now you can solve the question very easily. So you say, okay, if this is, you take this, then you say CB now, the new capacitance for the capacitor B will be simply half CA over 2 C0. And then depending on what you're looking at, if you're looking at CB over CA over CB, then it's half. If you look in the other way, it's twice. So, and that's, as I said, the reason I canceled that, because, oh, sorry, just 1 second here. The reason I canceled that because I did not give you this piece of information. So that's the first question that people ask me, and I mean, you were not penalized for that, so that's fine. The second question, which is basically the question that I guess there was a mistake, or at least when we graded it, there was a mistake in the questions and then the answers or you submitted, and that was this question here. Yes. this question, which one? It's question number 16. Before I go to question 16, let me just discuss this question here because there was an issue also with this question here. Now, a lot of you did not get this question here. This is the one that I'm referring to. And in this question, I think there are only 2 students who got the answer right. And if you look at that in this question, what the question is asking you is that you have all these charges distributed on a ring, and he wants you to find the direction of the electric field when the magnitude of the charges are the same at this point here, P. That's what he wants here. Now, if you remember, I talked a lot about symmetry. So I talked quite a bit about symmetry. And I said one of the things about the electric field is that it's symmetric. If it is uniform around some point, it's isotropic, and then meaning that it's the same in all directions. So if you look at all of these charges, if you look at this one here, remember to calculate the electric field, I have to place a positive test charge here, a small positive test charge here. So that means if I look at this, that the electric field will be this way. If I look, the electric field due to this one will be this direction, and they will cancel. So these 2 will cancel, right? If I look similarly, if I look at this one, the electric field, this is positive, this is negative, so it will be this way. And this is positive, this is negative, it will be this way. So these 2 guys will cancel also. And similarly with this one, the electric field is this way, and the electric field is this way, attraction, because positive and negative attraction. So all of these guys will give me 0, except this one. This one, the electric field, due to this one, because this is negative and this charge will be positive, so the electric field will be somewhere directed this direction. And as I said, there are only 2 people who got this question. So that's the second question that that I need to explain or go over. Question 16 now is the one that some people asking me, or a number of you are asking me about. Okay, it's this question here. Okay, so what does this question say? It says that he wants you to calculate the wavelength of an electromagnetic wave or saying that the wavelength of an electromagnetic wave has a frequency 256 hertz. And he wants you to compare it with the wavelength of a wave that has a frequency 512 hertz. Okay, and then there's half there or twice, so let me just go to the whiteboard and explain this again. So if I go here now, remember this is an electromagnetic wave. So V for any electromagnetic wave is simply c, the speed of light. Okay, and I know that V is equal to lambda f. Okay, so lambda in meters, f is 1 over second, so meter per second. So that's what. So then I have c. This is equal to a constant now, but the f's are different. The frequency is different. So if I take lambda 1 f1, which is let's just lambda 1 f1 is equal to c, and it's equal to lambda 2 f2 because c is constant. Okay, c is the speed of light. It's an electromagnetic wave is constant. So lambda 1. All right, f1, which is equal to 265, right? And it's equal to lambda 2 multiplied by 512. So it depends on what he wants. If he wants lambda 1 over lambda 2, then I have that's equal to 512 divided by 265. And if he wants lambda 2 over lambda 1, so this is how you solve it. And I don't know what the question is asking, but this is what how you solve that. And depends, as I said, if he wants to know the ratio of lambda 2 to lambda 1, this is how you do it. If he wants the ratio of lambda 2 to lambda 1, then it will be the opposite. So these are the 3 questions that I wanted to go over before I continue with the lecture. And hopefully then you'll at least you'll get them, you know now, you understand, and I'll fix whatever the mistakes that you guys submitted to me. Okay, so let's go back to the lecture now. Okay, so back to the lecture. And if you remember, last time we were discussing, we were discussing lower hand. Okay, that's fine. Oops. We were discussing the magnetic resonance imaging, and we got up to this slide here. Where is it? Okay, up to this slide here. Okay, so this is where we were last time, and okay, I see Nawal is raising her hand. Is there an issue? No. Okay. Because you can actually, if you're watching me on your iPad or on your mobile, then there is a feature here at the bottom. I think you see it here at the bottom, the hand. Then you can click on it, and then that will give you sort of will allows you to ask questions during the period. And inshallah, next time we'll do that. So anyway, so let me just go back to what we discussed before. And what we said that we defined the resonance frequency, if you remember, and we said that the resonance frequency, if is actually defined by the gyromagnetic ratio, gamma. They want to ask me some questions. Yes, they want to ask me some questions. Why don't you answer the questions, Nawal? These are about the exams, right? About the questions in the exam, right? I can pause for a few seconds so that they can ask you. Okay, they can ask you questions. Go ahead, and when you finish with them, let me know. Listen, just in case, I will correct the exam or the questions as per the question. So if the question is asking lambda 1 over lambda 2 or lambda 2 over lambda 1, I have to correct whatever the. But if there are questions about the capacitance, the questions I answer, then that's fine. Want to write to write what? Okay, that's fine. If they want to write me questions, that's fine. Are they watching me on the? I guess they're watching me on the main screen. Okay. Are you going to count the second question? Which question? No, I'm not counting the second question. No, I said the second question is missing information, and I will not count that. So let's go over this. Let's just forget about the questions about the exam and count this and count that, which we'll never finish on. So, anyways, let's go back to our discussion of MRI, and let's start where we left last time. So, all questions related to the exam, I'll entertain them after I come back on. Okay, so let's look at this is where we left last time. Remember what we said about MRI. MRI is based on the movement or the motion of the protons in the nucleus, where we said that a proton is precessing, and if you remember, the precession is simply a coupled motion that is comprised of two motions. One is revolving around itself or rotating around itself, and then the second one is rotating around the central axis or the axis of rotation. So this is why protons are considered as a magnetic moment. Okay, magnetic moment, that means they are magnetized in nature, and if you apply a magnetic field, as just like what this point is saying here, if you apply a magnetic field, when a magnetic field is applied, then the moments will align. So they will just like there would be very small magnets. So that's now what we wanted to discuss next. You don't understand what? They don't understand what? What I'm saying here? We explained this many times then. Are they asking about the lecture or the exam? The exam, forget it. I'm not going to answer any more questions about the exam. Slow down. Okay, that's fine. Slowing down is not an issue. Okay, so now I guess the previous slide, we already talked about this and we discussed it very, and that was where we concluded last time. Okay, that's where we concluded last time. Okay, fine. Now, this is where we're going to start today. We wanted to talk about something called the net magnetization. If you look, this is what we did last time. We said that these protons are actually randomly oriented. Hopefully now I'm going very slow. Now I understand because of the lag and the okay, so these guys are randomly oriented in nature. Okay, there are so many of them, and they are randomly oriented. Once you apply a magnetic field, this is what a magnetic field means, okay? Represented by a vector here. Once you apply a magnetic field, then some of them will be aligned, okay, and some of them will be anti-aligned, or let's say some of them will be parallel, aligned parallel to the magnetic field, and a few of them, and if you remember, I said a few of them will be anti-parallel, will be aligned anti-parallel with the field. Now, if you sum up these guys, if you sum up all of these guys, let me just erase this again. If you sum up all of these guys now, if you sum all of these guys, these will cancel, okay, treat them as vectors. And then you have these two will cancel, and then you have two vectors pointing up, and that's why you have a net magnetization that is pointing along the field. Make sure, write this down. So the net magnetization, there are two things about the net magnetization. It's not equal to zero. So number one, it's not equal to zero because there will always be more vectors or more moments pointing in the positive direction or in the up direction or in the parallel direction than pointing down or pointing in the anti-parallel direction. Because of that, as you can see here, you have 1, 2, 3, 4 up and 2 down. So that means the resultant here is actually 2. Remember the resultant in first year? The resultant? So the resultant of these vectors is 2, and it's pointing in the positive direction. And this is what's so-called the net magnetization or the net magnetic moment vector. Okay? So the idea here is that the net magnetization is not equal to 0, as I've stated here. And number 2, it's pointing in the positive or in the up direction. I should say the positive direction, in the up direction, because that up means something in physics. Okay. Now, okay, so now I have a net magnetization. I went from 0 net magnetization here, okay, to a non-zero net magnetization here. Okay, how did that come about? This came about when I applied the magnetic field. As I said, we called it the static or the uniform magnetic field B0 that I applied at the beginning of my MRI. Okay, so just make sure you understand. Okay, now I have, once I apply the magnetic field, then I have a net magnetization that is pointing up. Okay, and it's not equal to 0. Just to remind you what is meant by pointing up, or what is the significance of pointing up, we said that there are more up. These guys, there are more of them up, right, than down, simply because up is the lower energy state. Lower energy state, that means, if you wanted to put it in general terms, that means the protons in general are lazy. They want it to be in a lower energy state where they don't have to fight the excitation energy, just to make it, simpler for you to understand. The excited state is the one, the guys that are pointing down are in the higher energy state. I shouldn't say the excited state, but the higher energy state, they will be down. But when I apply the magnetic field, B, this external magnetic field here, B, when I apply it, then I will have a non-zero It's running from my side. Okay.
Okay, Doctor, you can start now.
Okay, I guess Nawal gave me the green light to start again now. Okay, so let's see where we left. We left at this point here, where this is the patient here, where all the protons, as you can see, they're randomly oriented. And by the way, everything we do from now on, we will be considering this here, the long axis of the patient. That's where the magnetic field will be pointing. So the external magnetic field, the static external or the uniform magnetic field, the one that I turned at the beginning, it will be along the the axis of the height of the patient. All right. So as you can see here at the bottom picture, as soon as you turn the magnetic field on, then your magnetic moments, the protons, will be aligned or in the parallel and in the anti-parallel direction. And this is, as I said, just a depiction of what we talked about, about when you apply the magnetic field, you get a net magnetization that is not equal to 0, okay? And that is, in this case, oriented. Remember, I said I don't like the positive, the fact that it's along the positive direction. No, it's just pointing along the field. Just whenever we say that the net magnetization is pointing along the field, it's not equal to 0, it's pointing along the magnetic field. Okay, next. Now, we wanted to talk about something called RF, because remember, MRI, the M stands for magnetic, R stands for resonance, or resonance frequency. So, MRI, resonance frequency, and the I stands for image count. What is meant by resonance frequency? Now, if you look here, if you follow what I wrote here, resonance frequency occurs when the nucleus, meaning the proton, resonates or tunes in when the magnetic field is applied. So if I wanted to put it in simpler terms, that means when I have a resonance frequency, let's say a frequency applied, an RF, if the frequency of this applied electromagnetic wave is the same as the frequency of precession. Remember, this is the proton that is precessing at some frequency f, which is defined by gamma b, right? That's what it defined as. So if I apply an external radiomagnetic or electromagnetic wave that has the same frequency as the precession frequency, if this occurs, then we say this is resonance. So they are both resonating, or they both have the same frequency, the precession frequency and the external. And I say external because this is the one that you apply, the resonance frequency, you apply it externally. And I'll show you how we do that in a minute. If this condition occurs, so resonance occurs, so that the frequency is the same for both, then energy can be transferred, or at least energy can be exchanged back and forth. Okay, meaning what? Meaning that this magnetic moment, that the net magnetization, now it can gain energy from the RF. Okay, gain energy means something. Gain energy, that means it will go from the lower energy state to the higher energy state. That means it will, we say in physics, it will flip. So it will flip from lower energy to higher energy state, or to higher energy, to higher energy state. So let's just read this, and then I'll open a whiteboard to talk about that. Nuclei in general is extremely sensitive to RF signals that have the same frequency. Okay, so if the frequency of this EM wave that I'm going to generate externally is the same as the frequency of precession, then there is an exchange of energy. Okay, exchange of energy. That means this guy here, the net magnetization M, the big M that I got because of the application of the magnetic field, it will have the chance to gain energy. Resonant frequency, just generally, it's called the Larmor frequency, and I think I mentioned last time, it's just simply because it was named after the scientist who invented it. So let me just open a whiteboard here to just talk about this. So the idea is that I got my net magnetization here, capital M, right, which is not equal to 0 because of the application of a magnetic field B. Okay, and remember, M, it has to be the same and the same direction. The net magnetization has to be the same direction as B. Okay, and go back to slide 1. Okay, let me explain this first. And I'll go back to slide 1. Okay. Now, okay, so this is the, because I'm trying to explain this now. Now, once the idea is this big M here. Now, it's processing. Its actual natural motion is something like this. Okay, it's something. This is the magnetic field, the direction of the magnetic field this way. Okay, that's B, and it's precessing this way. So it's doing this. That's what it's doing, okay, continuously. Now, when I apply an RF, so this is now I am applying an RF, which has the same frequency as the Larmor frequency, F Larmor, which an F Larmor is simply gamma. setting from my magnetic field B, from my magnetic field, I can find, I can calculate the Larmor frequency, which is that. Now, then after I find this, I apply my radio frequency, which is set as the same. Let's call this Larmor. Okay, so I set that I set my frequency, my radio frequency, using this conditioner. After that, as soon as I turn it on, as soon as I turn this on, this, because the frequency is the same, then this net magnetization here will gain energy and will start to go to the excited state. Okay, so it will start to go to the excited state or the higher energy state. That's the first idea. Now, what happens if I turn this off? If I turn this, go to 0, then because this guy here now, let's just suppose that it's here somewhere, right? Gained energy and it's flipping down, and I turn this off, I turn the frequency off, then what is it going to do? It will go back to its original state, okay? Now, going this way, it will gain energy, right? Going this way, it will lose energy. So the energy, it will gain it from the applied RF, because the RF is simply an EM wave, right? Okay. Is that better now? Okay now? Okay, so that means we have to have a camera as well now. Should I repeat from the beginning? Should I repeat? Yeah, okay. Let me erase this then. Okay, so again, and this is for your own benefit. So now, because this is very, very important now. So I got my net magnetization that is continuously precessing around like this, and my magnetic field is this way. Okay. Now, once I apply my radio frequency, or apply my electromagnetic wave, which is simply has an energy E is equal to H times F, and this frequency here is must be equal to the Larmor frequency. Okay, so these two must be equal. If they are equal, then the magnetization will gain energy. The net magnetization will gain energy, and in doing so, what it will do, when it gain energy, it will go to a higher energy state. So it will move into a higher energy state, and we say it will flip. Okay, so this is the lower energy state where it's doing this way, this motion here around some axis here, right? And now it will flip, so it gains energy. Now, okay, so this is an energy gain. Now, what happens if I turn this off? If I turn this off, then this guy, which was here somewhere, right? Which was the magnetization, which is now, instead of MZ, along Z direction, because remember we said this is all of this is the Z direction, the long patient, or the axis, or the long axis along the patient, right? Now, if I turn this off, then this will relax back, okay? Relax back to its original. So in here, it gains energy, okay? It gains energy. Here, it gives off energy, gives off energy. So gain energy, gives off energy. When will this happen? If I turn this if the frequency on, it will gain energy. If I turn it off, it will lose energy. Gain energy, lose energy. Lose energy, that means what? That means it's going to give me off some energy that I can detect here somewhere using my detector, as I'll see in a minute. Okay, this is the basic idea of MRI. This is the fundamental idea of MRI. You apply a magnetic field, okay, and then once you apply a magnetic field, you end up with a net magnetization that is not equal to 0. And then after that, you apply a radio frequency, which is, it has to resonate with the precession frequency. So it has to be the same as the resonant frequency. Once that happens, then the net magnetization will flip, okay, will go to a higher energy state. If I turn it off, it will go back. So the idea is that gain energy or absorption of energy, and then when RF is off, when RF is equal to 0 off, then it will give emit energy. Okay, gain, emit, and that's what we are. Now, what we wanted to do, we wanted to capture this. That's what we wanted to capture for our image. For our MRI image, we wanted to capture this emitted energy. The emitted energy is in the form of an electromagnetic wave with some frequency that depends on the proton concentration. So how many of these guys have? What is the net magnetization? Let me see if this can be explained here. Okay. If I can explain it here in the slides that in the PowerPoint. So Nawal, you can ask them if the idea of the net magnetization is clear, and if the idea of what happens, once the net magnetization or once you apply an RF. Yeah. So you can follow this picture here. Okay. So initially, as you can see, initially you have something like a lot up, okay, and a few down. The net magnetization is these guys, okay, and these are precisely like this. Once I apply a magnetic an RF, then I have a flip to the anti-parallel, okay. Now, just before I go into the relaxation and magnetization and all of these things, there seems to be a question. Can you summarize what you explained? I will summarize it in 5 minutes. I just need to go over 2 slides, and then I will have a nice summary of what I just said. Now, remember, I said that turn on, turn off. Okay, turn on, that means I turn on the RF signal, and then my net magnetization will be, let's just say, excited, okay, gains energy. And then when I turn it off, it will go back to equilibrium and it will give off energy. Now, that energy which is given off is what I capture. That's the most important thing. That what I capture is the most important thing. Now, I'll discuss this later on when next time I see you in class. So that energy that is given off, right, which is called the emitted, let's say the emitted energy. If you look at the electromagnetic spectrum, the MRI or the window for NMR in general, or MRI. Remember I said MRI, NMR. It's a sort of a mixture of both. It's somewhere here. And the reason it's highlighted here, this is the radiation, if you want to call it, if you want to use the term from X-rays, this is the given off radiation. What is this? It's way below the ionizing. Remember, this is the ionizing energy. So anything here above is ionizing energy. So what we say that the energy given off in MRI, it's way lower, much lower than the X-ray, or than it's not in terms of ionizing. In fact, it's somewhere closer to probably even visible light, or below visible light. What is this? What is the significance of this? Significance of this is that this makes MRI very safe in terms of radiation. And remember, we talked about radiation, the effect of radiation, and all of these things. And we'll talk about X-ray when we talked about X-rays. So this makes MRI very safe procedure from that aspect. Again, I'll come to. So let me just talk about excitation versus the relaxation, and then I can go back, or I'll go back and summarize. So excitation, when the RF wave is applied to the material, okay, at the presence of the magnetic field, some of the energy will be absorbed by the individual nucleus. The excitation will flip away the alignment of the nucleus and put it in the excited state. Okay? So I apply a magnetic field, I calculate its precession frequency of the net magnetization, and then I apply a radio frequency at the same similar or not the same exact number or the same exact value as the Larmor frequency, and this will give me or will lead to a flip away of the alignment. Now, okay, the nuclei will experience an increase in torque as it flips away. So this is originally here. As it flips away this way, then the torque, which is basically because of the angle, it's just like you're trying to extend a spring. The more you extend it, the more it wants to go back. The more you try to extend it, the more it wants to go back, right? And torque from the magnetic field, and in an attempt to realign it back with the, eventually that will occur. So the nucleus may only return to its original alignment with the magnetic field if it gives off energy. So in order for this guy that is now in the excited state to go back here, it must give off energy. That energy is our emitted electromagnetic wave, and that is the one that we're going to use to capture our image. Okay, let me see if I can find the next one. Okay, this is excitation, and this one we cannot see it here. Okay, this is the picture that I wanted to show you. Oops. Okay, this is the picture that I wanted to show you. Now, okay, so this is my patient. This is my patient here, and this is my magnetic field. Okay, I apply my magnetic field, and then I add a radio frequency here. I have a coil here, secondary. It's called secondary coil in MRI terminology, and that frequency or that coil, it just goes and excites the magnetization. And as it's excited, the torque increases. You know what torque is? Torque is just like force but rotation. Okay, when the object is rotating around a pivot, and then eventually it will go back. When it goes back, it gives off energy, and that energy is captured by the secondary coil. So this will register this as a signal, and that signal, the strength of the signal, actually is transformed into an image on the grayscale, which I'll explain later on. So this is what MRI, the way you can explain it using this picture, this very famous picture. I'm sure you've seen it somewhere. That first, this is my patient, right? I apply a magnetic field. Okay, that's the S and N, and then so this is my B, and then what happens is that I will have a net magnetization that is not equal to 0, and that net magnetization will be recessing, as I said, at some frequency. When I apply a frequency, a radio frequency at some energy, this guy here will gain energy and it will flip away. Flip away, that means it goes from the low energy state, low energy state, to high energy state. Now, this is not favorable. I said many times, this is not favorable. Because of the increased torque, this guy will eventually go back. When it goes back, it gives off a signal that is captured by this coil, and then the RF signal here detected, it will go to something called the image reconstruction, which is a purely engineering procedure, and which we'll not discuss. Okay, let me go back to the whiteboard and summarize to you, because remember, also today, before 8 o'clock, before 8 p.m., or let's say, just be more generous here, let's say before 10 p.m., I want every one of you to send me at least half-page summary of today's lecture on my Gmail. So on my Gmail, which you have, all you have it, just send me one half-page summary of what we did, which I'm going to capture. I'm going to go over now. Okay. So again, let's just summarize. So start with the random orientation. So if you want to start your summary, now you can take some notes. Start with random orientation of the magnetic moments in our tissue. Okay, so they're randomly oriented. You can learn. And make sure that if you do that, make sure you indicate that there are more up than down. So I'm going to here just simply 2 down and 1, 2, 3, 4 up. Okay, so this is the natural, you know, you and I walking around, there is nothing special about us. When you are when the B magnetic field is applied, these guys will flip. Let me change I think there is change color here. Colors, oops. Oh, okay, there's colors here. I'll go with red. Okay, so now these guys will be flipped along the, oops. Okay. They will be flipped along the magnetic field. So this will be up, this will be down, this will be up, this will be up, this will be up, this will be down, this will be up. So this is after I apply the magnetic field. So these two guys will cancel. These two guys will cancel, and I have 1, 2, 3. It depends on whatever your units are. Okay. So the idea here is that once I apply the magnetic field, then I have a net magnetization, net M, that is not equal to 0. Okay, and that is precessing. Make sure the net magnetization precessing at the Larmor frequency FL, which is equal to gamma B0, and this is my B0 here. Okay, let's call this step number. This is step number 1, where they are randomly oriented. This is step number 2 when I apply the magnetic field. Okay, I'll pause for a few seconds so that you write this down now. So this step number 1, where the magnetic moments are randomly oriented. Step number 2, I apply a magnetic field B0. And then what happens is that all of these guys will be, or not all, but they will be either aligned or de-aligned, and I end up with a net magnetization that is not equal to 0, and it's precessing at the Larmor frequency. Remember, the Larmor frequency is very easily calculated because I set this. Remember, I set my B0. That is the one that I told you that it's from, you know, somewhere 1 to 3 Tesla. That's the magnetic field that is used in MRI imaging. Okay, so that's step number 1. You can take a picture if you want. Okay, step number 3. Okay, so step number 1, step number 2, step number 3. Now, once I have them aligned, then apply an RF signal. Okay, now RF signal, there are 2 things that you have to know about it. First of all, F must be, the magnitude of F must be equal to the magnitude of the Larmor frequency, which is equal to gamma, the gyromagnetic ratio, multiplied by V0. And that's number 1. Number 2, so okay, they apply the RF. It must be this, and it must be external. Okay, external means what? Means that it has nothing or no relation to the magnetic field. It has nothing. It's a completely different circuit, and there is a reason for that. But let's not. That's not none of our business. But just make sure that it should stay external, and then it has the same value as the Larmor frequency. Once I apply that, what's the result of all of this? The result is that M, the net magnetization, M net, will gain energy. Okay, where is this energy it gained? Then make sure that I will look for this point here. It will gain its energy. It will gain its energy from E equals to HF. Okay, this is the radio frequency. This is what it gains its energy from. This is the amount of energy gained. When it gains energy, again, I will pause for a few seconds so that you either take a picture or write this down. Okay, so when it gains energy, the net magnetization, when it gains energy, it will go to the excited state. So it will be excited. okay, meaning energy. Now, once it's excited, let's just say that it's here now. It's flipping and still doing this business of precessing, still doing that here. Once it's flipping, the torque, it will increase on it, and it's just if you have a spring, and you try to stretch it, you stretch it. The more you stretch it, the more the force will be increased. So F is equal to kx. Remember, if x increases, F will increase, and then what happens that if you're not strong enough, then it will spring back. This is what happens here. The torque will increase to some point. At some point, it will spring back. Okay, it will go back, spring back. That means it will go back to the original situation. In doing so, it will give off another RF. Okay, so this is emitted, and this is absorbed. The RF, the first one, RF, is absorbed. This one is at frequency FL. Now, this one, the frequency, we don't know. We don't know what this frequency is. That's in fact what we're going to analyze. We need to analyze that in order to. So this emitted frequency here is captured. This is my detector here, and this signal here, or this frequency RF signal that is emitted, this is the one used to capture the image, the MRI image. Please make sure you do that when you mention in your summary. This is what you need to say. Gain energy, goes to excited state, flips back, it gives off energy, and that energy goes to this detector here, and it's detected as a signal, and that signal is transformed into a grayscale. Okay, the higher the energy, the darker, or the lower the energy, the darker, whatever protocol you use for your image or your image reconstruction. Okay, I think that's clear. So now, Nawal, if there are any questions, I can entertain questions now. Okay, I think the summary is very clear. نعيد كلها؟ الله يرضى عليكم، هذه ما يغني، هذه مسجلة عندكم. Sorry. آخر شيء. Okay, I will do that again. All right, now I think the idea, I'm very sure Ms. Nawal will tell you this, even some physicists, they have some physics students, they have difficulty understanding this, so you shouldn't feel alone in terms of comprehending what's going on. In fact, I have some animations that will help you understand this next time I'm in class. So let's start. I think the idea of alignment and de-alignment were beyond that. So I think up till here, where I have a net magnetization M, I think everybody should be, and my B is here, everybody's in peace with that. I don't think anybody should have any problem. I think the problem starts when you apply the RF, okay, your RF. Now, remember, RF is external, and the frequency of the RF must be equal to the Larmor frequency. And the Larmor frequency, FL, is equal to gamma B0, okay? So these are the conditions that you have to keep in mind. Once I do that, so that means the frequency of this guy, okay, which is Larmor frequency, is the same as the frequency of this wave. That means I have something called resonance condition. Okay, you should write this down. This is a resonance condition. When these two guys are equal, I have a resonance condition. What happens in the resonance condition? Energy, this energy here, carried by the RF signal, which is simply it's equal to HF. The net magnetization can actually absorb this energy. So this here can be absorbed by the net magnetization, and in doing so, because it's gaining energy, it goes from a lower energy state to a higher energy state. Some higher energy state, it will flip. Because remember, this is the low energy, and this is the maximum energy on the other side. This will be the excited state. If I have something like this that will be in the excited state. Anything in between, we call them the gaining energy. So it will gain energy, it will gain energy. This will be called MZ. And if it is here somewhere, we will call it MXY, simply because it's in the XY plane. So this is the Z plane, and this is XY. So if it is here somewhere, when it is at 90-degree angle, we call it the XY. Don't worry about the XY and Z. I'll explain it next time when I talk about the excitation and relaxation. Okay? So anyway, so now, again, let me change color. I'll go to green. All right. So once I have this situation, which is the resonance frequency, then the net magnetization will be excited or will gain energy. It will not continue to gain energy forever. At some point, it will flip back. Okay, it will flip back. If it flips back or it goes back to its original one, it gives off energy. That energy is detected by a coil called secondary coil, and that is detected in the form of some electric signal. Okay, electric signal. And that electric signal is what we use to get our image. Okay, I don't think that I can explain more than this, but remember, guys, you have this recorded. So as soon as I finish here and later on, I will post it on the Blackboard, and the full lecture, including my conversation with Ms. Nawal, including my hi messages, including everything, it's recorded on. So don't worry about missing anything. All right. All right. So I wanted to finish at least two more slides. Okay, so let me just very quickly, one to one. Okay, now let me just very quickly go to one of the slides that I wanted to capture, and then I think we'll be almost done. It's almost 12 o'clock now. All right, so we are. These slides contain a lot of animations. Next time I'll show you, and then they'll make things, for example, the resonance and so forth. Okay, so all right, fine, we did that, we did this. I explained this very well. Okay, so okay, let's go back to this slide here. Okay, so now this is when B is applied. So this is when only B is applied. This is my B here, okay? And then when I apply an RF, this guy will be flipping this way, right? Even with the RF is applied, at some point, this guy will relax up. And when it relaxes up, this is where it gives off some frequency or some energy, and that energy, the one I capture. So this is a very good picture to use in your summary, okay? Now, okay, this one as animation will, okay, this we talked about. This we've talked about also. Okay, now I think I'm just going to start this, and then just to so that I set it up for next class. Now, at the beginning, okay, this is my MZ. Okay, MZ, that means the magnetization along the Z axis. Let me change to blue, because blue is, you can see it better. When I apply the RF, okay, this after applying the radio frequency, this guy here, the MZ, will grow, will flip over, and I have a vector transformation. Well, the concept is a little bit. Let me just use a whiteboard to explain this. Okay. Whoops. Cancel. Okay, now the concept is now, okay, so I have MZ here, and it's MZ came from the sum of these guys, these variations. Now some of these guys will be flipped the other direction. So what happens when I sum them up? I have now something called, this is my MZ, which is the magnetization along the Z axis. I have a growth of XY, okay, because this is my X axis, that's my Y axis, and this is my Z axis. At the beginning, I only have MZ. So when at T equals to 0, MZ is maximum, and MXY is 0. Now, I am very sure you're sitting there and you're looking at it and you say, what the heck is MXY? What the heck is MZ? MZ is the initial magnetization when you apply the magnetic field. So when you apply your magnetic field, the sum of the magnetic moments, that gives you MZ. Okay. But when you apply your radio frequency, some of these guys will be flipped over. So what happens, this becomes smaller because it loses some of the vectors. And then I have a growth of the MXY. Okay, so I have this guy is growing, the XY, the magnetization along the XY is growing. And this guy is getting smaller. Okay, this is what the MRI is all about. It's about the relaxation of this guy, the excitation of this guy, and then the growth of this guy. So because what happened, this guy is grow up to a minute where it will flip back, right? So this will relax, we say it's relax, okay? And in doing so, we have two things. I will explain this one more time. What's this? Okay, I will explain this one more time. Okay, so MZ and MXY. Okay, applying RF leads to growth of MXY and decay of MZ. So the magnetization along Z will become smaller, and this guy will become bigger and bigger and bigger. At some point later time, this guy will flip back. So that means this will decay and this will grow. I think this is confusing, and I'll stop here. It's 12:03 or 12:05. I will stop here, and then we'll pick this up next time, because the growth and decay is what is referred to in MRI as T1 and T2. Okay, T1 and T2. These are the essential parameters for any MRI image. So T1, T2 is the relaxation time. How long did it take this guy to go to 0? How long did it take this guy to go to grow back? So because this guy, remember, is losing and this is gaining. Eventually this guy will lose and this guy will gain. Again, it's a little bit confusing. So thank you very much, and a special thanks to Miss Nawal. Please give her a nice clap, and see you inshallah after the holidays. جزاك الله خير محمد. شكرا وبارك الله فيكم. This will conclude the session inshallah for today.